Thanks, Brady. Good afternoon, everyone. I'm Laxmi Prasad. I'm an extension water engineer in Agriculture and Biosystems Engineering Department at NDSU. For the next few minutes here, I'll talk about the basics of drainage water management and how that impacts like overall hydrology when we look into like agroecosystems or mainly agricultural fields. So a typical water year in North Dakota or most of the Midwest or Great Plains region, kind of growing season starts with mid-April or early April, depending upon the weather, the winter or like spring weather. So most of the frost will be out somewhere like early April. So that's when most of the planting or like agricultural management operations start. So, and that's the time of the year drainage is really important. Let's say if the soils are really flooded and it's hard to get into the fields to perform any plant establishment practices, having inadequate drainage will really slow down that process, and producers many times lose that growing season. So whether it's a short season crop or whether it's a long season crop, drainage is important early in the season and also late in the season. In the late season, it really benefits with harvest and crop maturity. Lack of drainage during these critical periods really affects the overall crop productivity. I'm not saying we don't need drainage in between. So we need good drainage, and there should be sufficient soil water and enough air and oxygen that is hitting the plant roots. But these two periods are something that are really critical when it comes to drainage water management and when we look into a typical agricultural water year in North Dakota. So many of you might have seen these pictures, really standing water and, really saturated and flooding conditions in agricultural fields. And we all know what happens when we see this. There is decline in yield, a lot of different, wet-borne diseases, and overall it decreases the overall productivity of the crop. So why does this happen? This happens for several different reasons. One of the reasons is the field itself do not have drainage, proper drainage, like there is no either sufficient slopes to have enough surface water flow, or the soil has really poor infiltration or percolation characteristics, or the field might have really high water tables. So all these in combination kind of leads to really saturated water conditions or flooding conditions, which might affect overall crop productivity during the growing seasons. And subsurface drainage, or generally which is referred as tile drainage, is something most commonly suggested to deal with really saturated soil conditions or high water table soils or soils with really poor drainage characteristics. So tile drainage is nothing but installation of perforated tiles or plastic pipes, we can call, below the soil surface, so that excess soil water enters those pipes below the subsurface and they go out of the field, creating sufficient atmosphere for plant to really thrive and grow well. So it not only removes excess water from the field, tile drainage also benefits with redistribution of the entire soil water. They also remove salts and contaminants that are not favorable for crop, and they improve the overall plant health, soil conditions, and productivity. And in many cases, they also reduce flooding situations during or in between the growing seasons. So what is tile drainage? How, as we know, like what it does, but tile drainage mainly involves like three main physical components. I'm not going to go into the design process of this, but I'll briefly touch base on what it really looks like. So tile drainage systems mainly consist of three main components, like we can call submains or laterals. These are the pipes that run parallel to the field slope or along the field slope, and they carry water that enters into these pipes along the field slopes. And these laterals or submains are most of the times connected to a main line or a header tile. They take all the water that is coming along the field slope into the main line or header line, and this header line either is connected to an open ditch or a pump station to get all that excess water out of the field. And there are two types of drainage systems. One is conventional drainage system, which is kind of more common in this region. So conventional drainage systems, they are continuously draining excess water throughout the year. So whatever the water that enters the tile below the ground, it is taken out of the field. And in many cases, the water table within the field in conventional drainage systems is always below the tile line. But there is also something called controlled drainage. So the controlled drainage consists of like a control structure at the end of header line or main tile. So this control structure allows to hold some or all of the water within the field, not going out of the field. So these control structures can be increased or lowered depending upon what level of water we want to maintain within the field. So the question is, like, why do we need controlled drainage? So the controlled drainage really benefits. Let's see, we expect a dry spell within the cropping season. Draining all the water out of the field may not benefit the crop. Having a controlled structure, it will help to retain some of those water within the field. And whenever there is a dry spell, that water can benefit crops through the capillary rise or supporting the plant growth. Another benefit of controlled drainage is we can really target when to release that water, depending upon we're not impacting the downstream water quality. We're not really adding a lot of nitrates or other harmful contaminants in really high concentrations, so that this water is regulated or slowly released, that it won't affect downstream water. So I have a multi-state research project that is going on. We are looking into 4 different states, the drainage water management and also other agricultural management practices across the weather gradient of within the Midwestern states, how these management practices across the gradient are impacting the water quality. So one thing that is common across these 4 states here is corn soybean is some of the commonly produced crop in these 4 states. But however, if we look at the weather gradient across these 4 states, it's very, very diverse. If you can say, like, Ohio is like more of a mild winter, but we have like really cold and dry winters. So there is a natural climate gradient across these states, and we are trying to look how this climate gradient with same management practices is contributing to the hydrology and water quality in agricultural fields. So this project is dealing at 4 different levels. We're trying to understand the hydrology at a very controlled scale. And we are also looking to plot scale research experiments. And we also have edge of field monitoring sites across the 4 states. And we are also conducting hydrological modeling. So, but from the plot scales, the one question that we are seriously looking into, having subsurface drainage, how much effect does it have on the overall hydrology of the field? Having a subsurface drainage, does it change surface runoff? Does it really influence how much sediments, or does it really influence how much phosphorus we are losing in the surface runoff? That's one of the questions we are critically looking into with this plot scale research sites that we have across the 4 sites. So for this talk, I'll be discussing about the data we collected from South Central Minnesota. We have 6 years of data collected from South Central Minnesota, where we have like 2 field sites. One is tile drain and one is not. And we are monitoring surface runoff from the both sites. And the both sites have similar cropping systems, and they both have similar soil type. The only difference between the 2 fields is one is drained, one is not. And we are looking into having that drainage, how it is affecting the overall hydrology of the field. So these three bar graphs here, the one on the complete left, so we measure like annual runoff from these two sites, from the drained and undrained fields. We did not see anything significantly different on the annual runoff. Both sites have similar runoff, or like not statistically different runoff at the annual scale. But when we tease the data into frozen and non-frozen periods, the frozen period is something we are defining it as like November to April, and the non-frozen period is more like a growing season, which is from May to October. So even during the frozen period, there are noticed statistically different runoff, whether it's a drained or undrained field. But when we are looking at the growing season, that's where we are finding the benefit of drainage, which is increasing the surface runoff in the undrained fields, but having the drainage, it is reducing those peak runoff rates or like high flow runoff events. Though they're still not statistically different, but there is a trend that having drainage is impacting the surface hydrology of the field. And we further looked into having that decreased surface runoff, how that is benefiting sediment exports. So, especially during the growing season, decreasing those peak runoff rates, it is reducing the sediment concentrations at the edge of field. And we are finding much more less sediments coming from the drained fields compared to the undrained fields. And one thing I wanted to point out, why we are not finding anything in the frozen period runoff, no differences in the frozen period runoff, is in this climate, at least 60 to 80 days, the soil will be frozen, which means the soil water within the profile is in the form of ice. When the soil water is in the form of ice, it expands and it occupies more space than the water in liquid form, which kind of reduces the infiltration rates, while ice pores blocking those infiltration, or like water that is coming from snow melt or rain on snow. So that's one of the reasons, whether having drainage or no drainage, the infiltration rates are very similar between drained and undrained fields. That's why we are not finding anything in the frozen period, which is kind of affecting at the annual level. Through this project, we also looked into how much phosphorus that we are losing. Again, the particulate phosphorus is tied to sediments. So the more sediments that are going out, the more particulate phosphorus is going out of the field, especially in the form of sediment, through the sediments. And for the total phosphorus, particulate phosphorus is contributing to about 50 to 60% of the phosphorus that is going out is through sediment phosphorus, which is why the undrained fields have more total phosphorus losses compared to the drained fields. So one thing overall, we are still working on this data to kind of tease out few more critical periods, like especially for the Midwestern climate, although we say frozen versus non-frozen, there are transition periods between those frozen versus non-frozen. Soil is not completely freezing entering from fall into winter. There is a transition period. There will be partially frozen soils. They might be accommodating some infiltration, but we really don't know how much they're accommodating. And at the same time, when we enter from winter to spring, there will be transition phase where soil is only partially thawed or partially unfrozen, which might be accommodating some infiltration, but we really don't know how much it is accommodating and how drainage, what role does drainage have there. So we are further teasing out these data sets across all the states to look into those critical periods. Is that only the growing season where drainage is impacting the hydrology, or are there transition periods that drainage is also contributing to the overall hydrology? So far, this project that we are working on, having tile drainage, they effectively remove the excess soil water and benefit the crop growth. And depending upon, the rainfall or precipitation in the season, having tile drainage, they can add a few more days or to a week to the overall growing season, providing favorable conditions for planting or harvest. And tile drainage can reduce surface runoff during non-frozen periods, and the reduced surface runoff can also contribute to decreased sediments and phosphorus losses. But however, can having drainage really impact the overall hydrology of agricultural watersheds? That's something really complex to answer at this stage, because when we look into watershed scale processes, they are much more complex. What we are looking here through this project is at the field scale, but when we look into watershed scale processes, they might be bringing much more complexity, and it is not easy to answer. If we have drainage, it will reduce the flooding issues. It will reduce all surface nutrient exports. So those flooding issues at the watershed scale, what we see, they might be coming more from intense precipitation or catastrophic events. So that's something to further study. But at the field scale, drainage can impact surface hydrology, especially redistributing the soil water within the soil profile, and which might benefit reducing those nutrient exports and keeping the nutrients within the soil. With this, I'll stop. There are some drainage resources through the NDSU, and I'm happy to take any questions. Yeah. So the question is like, are we also looking into the nitrate or nitrogen related data? If I'm correct. Yes, we do have nitrate data or nitrogen data. We're still working on that nitrogen data because nitrate is kind of very volatile. I know many of us know. So the data, the way we are collecting these are cumulative events. We are trying to dissect them into events based upon the precipitation and snowfall data we have. But still, most of the data that we have is cumulative runoff. So we're working on teasing or like dissecting them into event wise and see when and where that nitrogen is really coming. So one thing through our analysis, one thing we can say that we are really finding those nitrate pulse in the runoff, especially when the soil is transitioning from frozen to unfrozen phase. So one process that might be affecting is, when soil is frozen, there will be microbial lysis, and some of the aggregates might be releasing that nitrogen or nitrate through sorption and desorption processes. Yes, we are finding more nitrate and ammonium also, but we are still analyzing to dissect those cumulative runoff into events and try to understand whether it is really coming from the frozen period or whether it is really coming from the non-frozen period. Yeah.
Follow-up questions. Have you looked at the water balance? How much water is moving horizontally through runoff? How much is
yes.
downwards drainage?
Yeah, we haven't looked into overall water balance because we don't know the overall boundary condition. We are still defining the boundary conditions to kind of quantify the lateral flows. No, we haven't looked into the overall water balance. That's something we'd be interested to see. Yeah, thank you. Yeah, I'll just repeat it for others. Are there any tools to kind of measure how to manage the control structures? So most of the times the control structures are operated based upon the water table, how deep the water table is. When we install control structures, we will also be installing piezometers is something we generally call, which help to know how deep the water table is. Is that 3 feet or 4 feet, 6 feet from the crop root zone? Or is it really close to the crop root zone? Let's say if we expect a dry spell and the current water table is like 5 feet or 6 feet. So the goal is to bring that water table close to the crop root zone. At that particular growth stage, let's say if the roots are like within 2 feet or 3 feet, then you can make the difference. The roots are at 2 feet and the water table is at 6 feet. So if you can add your control structure maybe 4 feet, so that can bring your water table slightly closer to the crop root zone. So a simple answer to you is measuring the water table kind of help to adjust the height of the control structures. And generally, when we install these control structures, you can know where your water table is either through piezometers, or these control structures itself can provide information on how deep the water table is. Based upon that information, you can adjust how deep you want so that your water table is close to your root zone. Yeah. Excellent question. Does drainage change overall hydrology? Within the field and watershed scale? Yes, it changes the overall hydrology because we are artificially taking away the water. It's not the natural process, but how much impact does it has? It's hard to measure at this point. There are studies going on, but it's the challenge with that is what is our boundary when we say in which area that is affecting hydrology, because hydrology is very connected. Even at the watershed scale, it's hard to quantify having drainage, whether it impacted water in this particular watershed or in a particular stream or river. A simple answer, yes, it affects, but the quantity that it affects, to quantify it is challenging. But one thing researchers have been using, or a lot of research that is looking into, is are we draining more nutrients through drainage? If you're putting more nitrates or phosphates through drainage into rivers and streams, that's something important to account for. Are we draining more nutrients into our water, which is benefiting our fields, but which might be negatively benefiting the freshwater resources? So that's when controlled drainage comes into picture. Rather than we drain everything continuously, we can control how much we want to drain so that we know what are the nutrient concentrations, and based upon that, maybe we drain during the high flow conditions so that whatever we are draining is reducing the concentration. It is getting diluted in a river or stream, rather than we drain during low flow conditions that we're putting more nutrients into the freshwater bodies. So that's one way to look into. But quantifying how it is affecting hydrology is a challenging question, because the challenge comes with the boundary conditions. Yeah, an excellent question. Yes. Yes, a good question. Maybe I'll just repeat for everyone. Can we capture the nutrients, mainly phosphorus and other nutrients that are draining? Yes. One way to do is drainage water recycling. Instead of pumping that water directly into the streams, there are practices like drainage water recycling, where we collect all the drainage water in surface structures within the field and use that water back for irrigation. That way you're cycling the nutrients and also using the same water. So that's one way. There's a lot of research going on. And the other way is bioreactors. So bioreactors are something, they could be placed at the edge of field where this water flows. And these bioreactors can capture some of the nutrients as they pass through the bioreactor structure and goes into the field. So that's another way. Yeah. Those are the two approaches that are being currently used to capture and recycle.